Oh, hello, ladies and gentlemen. After the setback in the previous video, I just felt the need to maybe come on live and talk about it. So, Hopfield Dictionaries are a dead end. We tried them out, and they worked really horribly. In fact, let me just show you how badly they worked. We have the logs here, and this is the enumerative Hopfield Dictionary trading. And this is the reward for PL0. And if it was optimal, it would be minus 0.08. So this agent is about 0.2 points per hand exploitable. And per 100 hands, that kind of comes up to 20 big blinds, which is incredibly huge. This is a very bad agent. And I think what we tested out here is a Hopfield dictionary with 64,000 columns. Okay, let's say 65. It's 64 in binary format, basically. When I tried it with like 500 rows, this was 0.5. So going to a higher number of rows, it does improve the performance. But the problem is that to get to the optimal performance that a single mutable dictionary with about 288 rows would have, it would probably require millions or maybe tens of millions of rows in the matrix. And this test run that we ran in the previous video took 2.5 hours to finish. If we put in like a million or 10 million rows, then it would require literally weeks to finish a single run. That the regular counterfactual regret algorithm with a regular dictionary would need only a couple of minutes, maybe even less. So it has, so it's very slow computationally. It's very inefficient, and it's basically an algorithm that isn't worth using. So the brilliant idea that I came up with is a complete flop, and the reason why is probably because it requires an exponentially many entries in the dictionary to approach mm, what a mutable update would do. The reason why counterfactual regret with mutable dictionaries is so efficient is because you can simply take the previous value and then average it out across iterations. But over here, we need to keep adding these entries and then average them out by going over the entire dictionary. So it kind of acts like an immutable dictionary with a limited storage space that overwrites all entries. And because it's acting like an immutable dictionary where we just add when we just continually add the new values, that's how we can imagine it. Just for a moment, imagine it doesn't really kick out old values once it goes over the capacity. It's a ring. It's basically the whole dictionary that we implemented is basically a ring buffer, and it constantly and it keeps acquiring more and more storage space, whereas the mutable dictionary can average things out directly. So that gives us a hint as to what is wrong and what we need to do to fix it. And here is what I think. What I think. Instead of this kind of implementation, where we multiply the keys by the input, then we subtract the constant in order to normalize it, then we take the exponential, then we multiply it by the values. Instead of doing all that, let's see, matmult softmax. This is how it was previously. Instead of taking the softmax, we'll just take the argmax. And once we have that argmax, we'll have an index, and we won't need to do that second matrix multiplication that used to be here. Instead, we'll just use the index to index into the correct row of the values matrix, and then we'll just get it like from a regular dictionary. Then we'll do the update, and we'll put it back into the matrix again as a mutable update. And in order to make this thing work, what we need to do is have a way of basically, you know what argmax is. It's a very simple concept. In fact, let me demonstrate it in something like Python. Do we have something like a Python script somewhere? Okay, here we have this script file. Okay, this one I want to keep around. Okay, let's do script file. Okay, so let's make a little array. 1, 2, 3, 4, 5. Let's make it into an numpy array. Import np. We'll turn this into numpy array. And then let's see, argmax. And when we run this, what do we get? We get 4. And then if we index into the original array using this argmax, what do we get? Then we get 5. The only problem with this is that suppose we have multiple 5s, and this could very well be possible if we do something like initialize the binary matrix all to ones. Then we don't want it to get the very first element all the time. We wanted to get probably the random elements from this array. What we could do is probably, let's see, we could, for example, do what I showed in the previous video in the F# script. I did this. This is take max function. And what it does is simply adds some. Sorry about this. In fact, I see that I cannot got rid of the random values. So what we do, this I is the integer of the array, this x is the element of the array, and this is now going to be a random number inside the array. And instead of take max, let's rename this to argmax. Now if we keep trying this algorithm again and again, you'll see that it gives us the different indices, all of which are 5. So that's what we need. We need to basically first sort by the argument, then we need to sort it by some random number that's inserted into the array, and lastly we just return the index. Okay, how we do something like that in Python? Okay, let's do mp ones like. Okay, empty like a, and then we random. Let's see. Let's do uniform maybe. 0, 1. And then size, okay, let's make it a size maybe. Do I need to do, no, I don't. Okay, let's do it like this. And now, Can we somehow zip the numpy arrays? Zip. Okay, let's ask ChatGPT. ChatGPT will do it for us. Okay, let's actually ask Claude. I haven't used that one for a while. I want to sort numpy arrays. Actually, I want to take the I want it to random, but when there are multiple max positions that have the same max value, I want it to randomly return the on those positions. Yeah, let's see what it does. Mm. Oh, actually, this is a good way of doing it. First it gets the max, then it just gets the values, and then it gets the random choice. Yeah, maybe. Yeah, I was thinking that. Yeah, we could probably do this kind of thing in again. If we were doing something like a CUDA kernel, I would instead do it more like this. I would take all the elements, then generate an array of random numbers, then do a reduction, do a max reduction that compares it like that. Uh, where? Oh, I didn't know that it had. Okay, let's just try it out. It's the F sharp script. Sorry about it. Random argmax. Yeah, it works very well. Um, so there you have it. I mean, at this point, this is the only thing that we could possibly try. We could start with maybe random projections or initialize all the fields to one, and then after the array gets updated, so, we could also do something to set the key at that particular location, because the key to be could be like something all 1 1 1 1 1, and the inputs could be like something like this. And then if the key is all ones, we want to set it to this key below after the update. And okay, this would actually be very easy on the CPU. On the GPU, it would be much more complicated. We'd have to keep tracks of like something like a gradient, and then update it using atomics. Then do a whole separate pass to update the array after that. But that would the expense of that would be nothing compared to the expense of having to do the large matrix multiplications. Uh, yeah, I had such great expectations of Hopfield Dictionaries, and then they turned out not to work. I mean, this is so difficult. Like at this point, what the human brain does might as well be magic. I just cannot seem to make a step forward into some kind of higher level of an understanding of intelligence, no matter how much I do this. At the very least, with this way of doing it, we don't have to, since we aren't using exponentiation anywhere, and are instead just getting the Rmax, the whole algorithm will be much more numerically stable. Like if you look at the previous algorithm, in the videos that I demonstrated it on, I've um, I've been using very low temperatures actually. Like over here, it's 0001, and that's pretty much identical to just using something like argmax. The main difference is that if there are multiple entries, they'll get averaged out. And that's a very important difference. Of course, if we have a large enough game, and we are kind of doing this KB and plasticity type of update that I mentioned here, then then that would not matter because in so no limit holding has like 10 to the power of 70 possible states. So different input would basically never happen. Even for Leduc, in Leduc we had a vector of 1143 entries, I think. Okay, let's look at the oh, sorry, I was wrong. It is 1312 entries. So that's 2 to the power of this number. And that's just for Leduc. Of course, Leduc doesn't have actually that many states. It has something like 1,000. But yeah, it's kind of a stupid example because in actual poker, this is just how many entries the vector has. But in actual poker, in in real poker, non in real poker games, you have a very large number of states that cannot be possibly represented in memory. So this so the array so the matrix will always be you always have unique keys, except maybe at the start. And at the start, that's where this kind of update will matter. Oh yeah, actually I forgot to turn on the video capture device. Okay, let's do this. Now you should be able to see me. Okay, it's very dark. Yeah, I will pause just now so I can so I can turn on the lights. Now you can see me. So what will we do next? Or, when these results came out yesterday, what happened was that it really hit me hard. So I had to actually go to bed for like an hour to recover. I didn't feel like playing games or anything else. I was just obsessed with it. And at this point, I'm actually halfway torn between trying out this algorithm and doing some trading systems instead. And in fact, my YouTube channel, after we've done with this poker stuff, is going to be about creating day trading systems, analyzing the stock market and so on. And this should be very interesting. I do have a couple of ideas for how we could day trade. I've read some academic papers on that, and I could probably replicate them, combine them with some of my own ideas. For example, over here in poker, we're currently trying to work on a memory system. We could take the same approach in the stock market and get something a lot better than than the simple indicator systems that are popular with retail traders. There's so many markets to trade, so many time frames, so many different instruments. It will be interesting to do that kind of research. But there is also I'm kind of in touch with a guy. We are both working on these poker systems. Maybe if I was alone, I'd probably stop here. But since I know some of you are maybe watching this. I'll do it for a little bit further. So in the next video, we're going to get rid of the Hopfield dictionaries, and we're going to replace them with what I call the max dictionaries. Max. Okay, this fused kernel will be a lot easier to deal with, and that's definitely true. I mean, at first we started out with the soft max, then we replaced it with the exponent, but replacing the huge matrix multiplication with just an argmax will make it so much easier to do all of this. Yeah, the difficulty has been cut into maybe a quarter of what it was, maybe even less. Figure out how they are going. Yeah. Oh, so sorry. You're still working on. You're still looking at my mug. Oh, this is what I wrote. I just changed the Hopeful dictionaries to max dictionaries and the mat mult to the argmax here. But it used to say mat mult soft max mat mult. I just changed it to this. Um, yeah, I guess we should get going. I think I need to take it a bit easier because it kind of stressed me out yesterday to see the Hopeful dictionaries performing so poorly. I need to take it easy, and it's going to all be done in like a month and maybe two or most. Oh yeah, also one more thing. What we're going to do, Slambot. I've been looking for ways of actually testing out the poker agents. And if you read counterfactual's great papers, you'll often see them testing it against Slambot. I wanted to find some different papers. I mean, some more up-to-date players, but they kind of, Noam, Noam Brown, they kind of keep their more advanced agents private. But this Slambot, I never actually tried playing against it here. Oh, you could probably play against it here. Okay, let's try it. Next hand, call, check, check. What's going on? Oh, I think it bet half a pot. Okay, let's raise half pot. Oh, it folded, I think. Oh yeah, Slambot folded. Oh yeah, this is very cool. But it also has this API. And what we could do is once we have our own poker agent implemented on the GPU, we could uh, we could test it against Slumbot, and this is going to be very helpful for us to actually know how exploitable our own agent is. Because once we implement subgame solving is going to involve continually retraining the agent at every hand. In other words, we're going to be doing a complete training run or every single action, not just on a hand, but in a game. So every time a player calls or raises or even gets a hand, boom, that's a completely new training run. And having to it's going if we are kind of have an agent that continually adapt to each other like that, it's going to be very very hard to know. It's going to be like it's going to be very hard to know how exploitable they are. So having something like a third-party bot that we could test against is going to be incredibly helpful. That's what I wanted to say. So yeah, thank you for staying here. The plan is going to have to change, and hopefully I can maintain enough motivation not to just drop this and go into day trading. See you in the next video. Bye bye.